This is section 11.3, which is more on limits. We're going to talk about defining a limit informally, properties of limits, limits of continuous functions, one-sided and two-sided limits, and limits involving infinity. Okay, so this is from, we saw this in 11.1, so we can write the limit as x approaches a of f of x is equal to L. So that says that f of x gets arbitrarily close to L as x gets arbitrarily close but not equal to a. Okay, so our first example is finding a limit. So we can find a limit graphically. So if we look here, this says that we're looking for the limit as x approaches 1. So here's 1, okay, of x cubed minus 1 over x minus 1. So if we look, we're looking at that point right there. We know that that point is not defined on our graph because we can't, if we plug 1 in, we would be dividing by 0, and we can't do that. So there's a hole there or something occurring that's not actually defined at that point. However, we could still have a limit. We can still have a value that it's approaching. So you can see from here, as we get closer and closer to 1, our y value is getting closer to 3. Okay, we can also look at a table. So you can see this table, we have 0.997, 0.998, 0.999, 1. You see there's an error, and we know that's because our function would not be defined at 1. And then 1.001, 1.002, and so on. And you can see from both directions, the left and the right side, we can guess based on the table that 3 would be where we're at for our y value at an x value of 1. We can also solve this algebraically. So if we can't directly substitute, and we'll look at some examples here in a minute where we can directly substitute what we're approaching, then we have other ways that we can evaluate it. So if we can factor in a way that we can cancel, that will allow us to evaluate the limit. So the limit as x approaches 1. So we have x cubed minus 1 over x minus 1. So x cubed minus 1 is a difference of cubes. It might not be one that you have memorized, but you should be able to recognize that that numerator is a difference of cubes. And we would factor it by writing x minus 1 times x squared plus x plus 1. And that's just the rule of difference of cubes over x minus 1. Okay, by factoring that, you can see we can cancel the x minus 1 in the numerator and the denominator. So then we have the limit as x approaches 1 of x squared plus x plus 1. And by factoring and canceling, we now can use direct substitution. So we can say, okay, this would be 1 squared plus 1 plus 1. So that would equal 3. So algebraically, we show that the limit is 3. So these are a whole bunch of properties of limits. So I did not write all of these down in the paper version of the notes, but you can definitely pause this video and write all of these down if you're interested in it, or you can always come back and refer to it later as you're working on your assignment. So finding limits by substitution. So we talked about in the last example, if you can directly substitute, you should. If you can't, you might have to factor or do other things to make it so that you can directly substitute. So on these examples, we can. We don't have an issue. So the limit as x approaches 0 of e to the x minus tangent of x over cosine squared of x. So that would be equal to e to the 0 minus tangent of 0 over cosine squared of 0. So we know that e to the 0 power is just 1. Tangent of 0, so if you think 0 degrees, 0 radians, tangent is y over x, so that would be 0 over 1, which is just 0. And then cosine of 0 is 1. 1 squared is 1. So this would just be 1 over 1, which is 1. And then our next one, Okay, we can substitute in the 16, so this would be the square root of 16 over log base 2 of 16. We know the square root of 16 is 4. The denominator, log base 2 of 16, that's saying 2 to the what power equals 16? Well, that would be 4. So that also equals 1. Not all limits are going to equal 1, but it just so happened both of those do. Okay, so one-sided and two-sided limits. So a function has a limit if the left-hand and right-hand limit are the same. They're equal. So that means you're approaching the same y value from both the left-hand side and the right-hand side. So for example, if you have a function like this, okay, and let's say that's at 2, this limit does not exist because from the left-hand side we're approaching one value and from the right-hand side we're approaching another value. So you can evaluate the left and right hand limits and find out if they are the same to determine if a limit exists at that x value. Okay, so finding left and right hand limits. So the notation you're going to see here, so see this is x approaches 2 with a little negative and x approaches 2 with a little positive. That does not mean it's positive and negative 2 because they are after the 2, that represents the left hand limit and that represents the right hand limit. So understanding that notation, for both cases we're going to plug in positive 2 because that's what we're finding. Okay, so the first thing says find the left hand limit and the right hand limit, and this is our function. So we're going to start with the limit as x approaches 2 from the left. So that means we're going to plug in, since this is a piecewise function, from the left would be x values that are less than 2. So we're going to use the top function. So we're going to say negative 2 squared plus, 4 times 2 minus 1. So that'd be negative 4 plus 8, so it'd be 4 minus 1, which is 3. Okay, then we're going to find the right-hand limit. So the right-hand limit would be where x values are bigger than 2. So then for that, we're going to use the bottom part of the piecewise function. So this would be 2 times 2 minus 3, which is 1. So these are not the same. So 3 and 1 are not approaching the same y value. So we would say the limit as x approaches 2, just plain 2, not from the left or the right, of f of x does not exist. Means it's approaching 3 from the left and 1 from the right. Okay, so limits at infinity. So we can also have graphs that are, we can evaluate the limit as x approaches infinity or x approaches negative infinity. So we're going to look at an example of that. So if f of x equals sine of x over x, we're going to find the limit as x approaches infinity and as x approaches negative infinity. So infinity, so as x approaches positive infinity would be this side. You can see that this is like the damping functions that we saw earlier in the year. So it's getting closer and closer and closer to 0. It's oscillating above and below that 0 line. So we can say that that is 0. And same with as x approaches negative infinity of f of x. That would be this side. As we go to the left, further and further to the left, it's getting closer and closer to 0. Oops, skipped a slide. Okay, and our last example is investigating unbounded limits. So you can see here we're finding the limit as x approaches 2 of 1 over x minus 2 squared. And so here's 2. You can see that this graph, we're not approaching a single value at 2, and it's going up forever. And you know, as like what we know about asymptotes, this graph's going to get closer and closer and closer to 2, and it's going to get bigger and bigger as we get closer. So we can say that the limit as x approaches 2 of this graph, so 1 over x minus 2 squared would be positive infinity, because as we get closer to that x equals 2 line, our graph's going to get bigger and bigger and bigger. Okay, so that is more on limits.